Alright, so you got a building, you got a steel beam, it's 6 meters long. At the end there's a cable at 30 degrees.
Mm-hmm. I'm trying to find if the worker should be worried.
He's 80 kilograms,
Mm-hmm.
standing 2 meters from the end.
Mm-hmm.
And the beam weighs 1450. Or has a mass of 1450 kilograms.
Mm-hmm.
Okay. Oh, and the cable can support a max force or max tension of 15,000 newtons. Should this guy be worried?
Mm-hmm. I didn't know what we would be looking for here, because I mean, I would imagine it would be torque, but there's nothing that's moving.
So no, there isn't anything that's moving. So it's a equilibrium problem.
Okay.
But if anything were to move, how would it move? Say the cable snaps, what happens to the beam?
It would go down.
But how would it go down? Yep. So if the cable were to snap, this beam would rotate about this point,
Yeah.
which means that would be a torque
Okay.
because of rotation. So it is a torque problem because the motion that would happen if it wasn't in equilibrium would be rotation. So we've got a moment arm, we've got forces, we've got a torque problem. So yeah, we will be summing summing torques. But what?
So it'd be a before and after type thing?
No, it's just you'll have a free body diagram and you'll sum the torques. But what do you want to solve for? Is the guy's weight going to change?
No.
Or the weight of the beam?
Not if he's on it.
No, so his weight and the weight of the beam, they're just set.
Yes.
But what happens if he gets off? Does the weight of the beam change?
Yes.
Well,
No.
it stays the same.
Right.
But what about the tension in the cable?
If he gets off, the tension would lessen.
Right. So this is what's changing, the tension. We have a max value for it, but we want to find out what the tension really is if he's out there.
Okay.
That way we can compare it to the max. And if it's greater than the max, he should definitely be worried. If it's less than the max, he'll probably be fine.
Okay.
Okay, so with this kind of a problem, with torque, free body diagrams are a little bit different because you kind of have to show the moment arms. So if it's like a disc, you can draw it this way. But in this case, it's just a beam. You can pick a point here. Let's call this A. And you just draw the beam.
Okay.
And then you put the forces on it. So what forces are acting on this beam?
Gravity
Okay, so where does the force of gravity act?
in the center.
So right at 3 meters, we'll have the force of gravity from the beam.
Okay. And then we have a normal going outward on the axis.
So right here.
Yes.
So we would have, you're right, there'd be a force here. Maybe just call this AX,
So we'd have the force
AY.
of the wall on the beam and the force of the beam on the wall.
Well, this is just for the beam, so we wouldn't draw the forces of the beam on the wall.
Okay, just for the beam.
These are called the reaction forces. You don't need to worry about them too much right now. But
Okay.
What's your major again?
Biochemistry.
Oh, you probably won't have to worry about these ever.
Okay.
Because reaction forces, this is an engineering thing. But in this problem, we'll see what happens to them. They don't matter.
Okay.
So we'll just label them AX and AY, and we're not going to worry about them.
Okay.
Okay?
I don't know what other forces are acting on the beam.
So,
I mean, I know the wall is, but...
So what is the construction worker doing?
Oh, the construction worker is pushing down on the beam.
So his gravity pushes down. So let's call this FG, maybe C, and FGB. B for beam, C for construction worker.
Okay.
So he's at, what's his distance from the moment arm?
4.
So he's 4 meters. And then what's the last force acting on this?
The tension.
Right. So we've got tension going this way, 30 degrees. And that's at another 2 meters. So a total of 6 meters. Okay.
Okay.
So now we can sum our torques.
Do we not worry about the wall? The wall's force on the beam?
I'll show you why here in a second. So sum of the torques about A. And which way do you want it to be positive?
Well, if my radius is this way, I wouldn't know. I would just do this. I don't know why I would do that, because I could. Oh, I'll do it this way. Wait, no. I would say this is positive because this is the way that it would rotate if it fell.
Okay. So clockwise positive?
Yes.
That works just fine.
Would you have done the opposite?
It doesn't matter.
Okay.
Because either way, so what'll happen is either the gravity torques will be negative or the tension torque will be negative.
Okay.
No matter what you do, you're going to move one to the other side. All right. Doesn't look very positive at all. So, with clockwise positive, what torques do you have?
I have 2 perpendicular forces. So I'll have torque 1 times the force of gravity on the no, I'll have 3 times the force of gravity of the beam plus 4 times the force of gravity on the construction worker.
Okay.
And then I'll have 6 times tension sine of 30.
Perfect. And
Oh, and I guess that would be negative because it's going up.
mm-hmm.
Would have missed that.
So if you were to try to sum the torques from these two, what would they be?
0.
Mm-hmm.
Question. With the tension, it's negative because why?
So we said that our positive was going this way.
Right.
The tension would cause it to go that way.
The tension would cause it, if there were no other forces, the tension's causing the object to go up.
Mm-hmm. So it would rotate it clockwise or
If
counterclockwise.
the tension increased.
Well, yeah, if the tension increased or if tension was the only. So you look at them as if they're the only force on the object, right? So if this was the only force, the object would rotate that way. If this were the only force, it would rotate that way.
Okay.
If tension were the only force, it would rotate this way, which means it's negative.
Cool. All right, so that's all of our torques.
Okay. And what does that all equal to?
So we'll have
Hopefully.
3 times 9.8 plus 4 times 9.8 minus,
Or before you go there,
okay,
so this will equal